Hello, Discrete Math. Mr. Mistakis here, doing a video lesson on Bernoulli experiments, the logical next place to go in probability. All right, this is another example that uses combinations. So what I'm going to do is I'm going to run you through a lesson that you're going to watch, and you can watch over and over again until it makes complete and total sense. All right. And by the way, Bernoulli's was a famous mathematical family in he was born in 1654, Jacob B., who is the guy who came up with this. It's attributed to him. So let's take a look at our first example to get the idea. Example 1, a fair coin is tossed a total of 4 times. And the question is, what is the probability that you get exactly 1 heads? All right, now, the way we would do this, well, in our previous experiences, we might make a sample space or a full tree, okay? But things can get out of control that way, so we're going to approach it a little differently. What we're going to do is come up with the simplest way to have this happen. Let's say you went heads, tails, tails, tails. So what we're always going to do is we're going to come up with the simplest, straightforward example. Usually you just have whatever you want happen first, and then next to that. Notice it's either heads or tails. So the full probability is, if this is half, this is the other half. So they basically add up to 1. It's a yes-no situation. Yes is heads or no, it's not. All right, well, this probability we would do with 4 slots, as you know. Probability of flipping a heads is 1/2. A tails is 1/2. A tails is 1/2. A tails is 1/2. This is 1/16. This is one way it could happen. Now, if we had a list, we would just count up the number of ways you could have 1 heads. We've done it before. You guys kind of know. The head could be here, 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 or here. So the second part of this is the number of ways to mix it up. The number of ways it could happen in this case is 4. The heads could be in 4 spots. So the full answer here is there's 4 branches, each of them at 1/16. And so we get 4/16 is our probability. All right? What we're going to focus on today is the idea that it's a yes or no situation. There's a winner and a loser, and together they add up to 100%. So yes heads, no heads in this case is tails. And the number of ways in which it happens times that. As you found from your trees, when you have a branch that has a heads and 3 tails, it doesn't matter the order. It's going to multiply to be 1/16 each time. So this is another way of counting up the branches of a tree. Right. Next example is a little more complicated. We have an unfair coin, for example, 2. So an unfair coin that has, let's see, 3 out of 4 times it's tails, and only 1/4 of the time would it turn out to be heads. So the tails side has been weighted. And the question we're going to look at is, if it's tossed 4 times, what is the probability of 2 tails, exactly 2 tails, in 4 tosses? All right. Well, our strategy for doing this is going to be, we take the simplest way for this to happen, and we go tails, tails, not tails, which is heads, heads. So think of that tails, tails, not tails, not tails. And heads is not tails in a coin, okay? Now, this would be 4 slots. Tails is 3/4, so each time. The other thing we should mention is this is a repeatable experiment. There's no well, you can't do anything that has no replacement. So it's like with coins, with dice, with spinners, things that just keep repeating the same experiment over and over again. You can't have the probabilities changing on it. It's not like pulling marbles out of a bag where the next time, since you have an orange in your hand, it changes things. It has to be a repeatable yes-no situation that this will work in. That gets us 9/16. Nope, sorry, 9/256. 4 times 4 times 4 is 256. And now we're interested in the number of ways that you could get two tails in this thing. This can be helpful to think of it this way. So let's think about the slots. I have 4 slots and I want 2 of them to light up at any time. That's where I should put the tails. And I don't want to double count things, and I don't care about order, okay? So what that basically means is 4C2. I want to light up any pair. And I don't want to count them twice because the order doesn't matter. It's not him, then him, it's a team of 2. So we have 4 slots and we want 2 to light up at any time. That's the number of ways that could be done. That's 4 factorial over 2 factorial times 2 factorial. That's 24 over 2 times 2, which is 6 ways. So you can trust me on that. You could also type it in. So here was the first thing. We found the probability of one branch, and we found the number of branches. And from there, we can do our answer. The probability is 6 times 9 over 256. So it is 54 over 256. So a little bit more than 25%, whereas this was exactly 25%. All right, so if we look at these examples so far, again, we've only been dealing with the coin. I want to do one more example before I put the formula up. This is going to help you see the connections, I hope, to all of it. So let's do example 3 now. It's a little different. But we're going to do it the same way, and then we're going to come up with a formula that makes this a lot simpler, and that formula eventually will evolve into a whole new sample space idea. And that'll be the end of probability and combinatorics for us. So here's example 3. Let's see, we are rolling a fair die. We roll a fair die. Now fair die means everything's equally likely. A fair die. And we roll it 5 times. We're asking what is the probability that 6 shows up exactly 2 times. So a 6 is a win, any other number is a non-win, okay? Now I don't have to worry about the fact there's 1, 2, 3, 4, 5 in the die. There's 6s and not 6s, and that's the best way to think of this because this is a yes-no situation. If you think about it, it's a 6 or it's not a 6, okay? And that's the only time we can use this soon-to-be-seen formula here. Well, let's do the simplest one. There's 5 rolls. Let's go with a 6, a not, and a not. That's the easiest way to start. Don't try to get fancy, just have your winning stuff happen first. Well, the probability of rolling a 6, I'll do this in red since I used blue there, 6s. I'm going to write these instead of the number because it gets weird. So we got a 6, we got a 6, and we got a not 6. All right, I don't need red then. 1 out of 6 and 1 out of 6. Again, repeatable, not changing because we've done it once. But a not 6 is the other 5. Okay? Now, I know the top of this is 125. I'm not sure what the bottom is, so I need to grab my calculator and do 6 to the 5th because I don't really know that number off the top of my head. So let's just go and do that. 6 raised to the 5th, 7, 7. So that's over 7, 7, 7, 6. Okay? Now, that's one way it could happen. Again, the 6s, think about the 5 rolls. 2 of them need to light up. That's where the 6s would be. We only want to look at the ways that could happen. Where could those groups of 2 be? That's why it's a combination. So we basically say 5C2. I have 5 slots. I want 2 to light up. How many ways can that happen? 5C2 is 5 factorial over 3 times 2 factorial. I'm doing this the old-fashioned way because I don't want to go for my calculator. So that's 5 times 4, when that cancels, over 2. So that's 10 ways. We multiply these. So 10 ways times the probability 125 over 776. That's saying there are, if you did a big huge tree, and I do not want to do a tree here, right? This would be 5 levels of it each time, 2 things coming out. It turns out there's 10 branches with this probability, which gets me 1250 over 7776. All right? So, what we're basically looking at here is this idea that we have the probability of a branch and the number of branches, and then we compute the thing. This leads us to a formula. Now, this formula is only applicable in cases where it's multi-stage, you do something more than once, It's also a yes-no experiment. We either win with a 6 or lose with a not 6. Flip a tail or a not tail, okay? All these different things. Basically, another thing you should notice is these two probabilities, 1/6 for the win, 5/6 for the loss, they always have to add up to 1. That means it's a complete closed system. 3/4 and 1/4. Example 1 was 1/2 and 1/2, all right? And what we're gonna find again is that we wanna multiply the probability of a branch by the number of branches, if you think of this as a giant tree problem, okay? Now, to do that is a pretty simple idea to come up with a formula. So that's what I'm gonna do right now. But we're gonna use n's and r's, okay? So, if you think about it, in n times, we want exactly r wins. That's what this is all about. We need a formula for this. In n times it's something, we want exactly r wins. Now, for the formula, we're going to have some other letters that we need here. Okay, so we have P equals this is little p, not a capital P, is the probability of a win. Q is the probability of a loss. And it's true that P plus Q must equal 1. Otherwise, you shouldn't be using this. All right? So, how does this work? Okay, well, here you go. Your formula has two parts to it. There's the number of branches, and there's the probability of a single branch, a single winner. The probability of a single winner will be, you want to win P, you want to win R times, all right? Which means that you will lose the rest of the times. And there's a total of n, you win R, that makes this n minus R. In other words, what's left? So think of this as win, lose, not lose, lose, that's not. Lose. And you want to win R times, which basically means if it's out of 5, you win 3, you lose 2. What's in front of here? Well, we want to know the number of ways R things could be winners out of n. So that's your formula. And that's what we've been doing. This is called a Bernoulli experiment because it's a very specific thing. There's basically multi-stage events, and we're talking about an exact number of outcomes we want. Those outcomes are yes, no situations. You can't do this if you're talking about spinning a 1, 2, or a 3, right? It has to be about a 1 and a not 1, or a tails and a not tails, okay? So that's a key thing here. Now let's put this into play in an example where we do the formula for it, all right? Fun to be back at the board. I haven't been teaching at the board in a long time. So we're going to call this example A because I don't remember what number I was on. This is one that's near and dear to students' hearts. You take an 8-question multiple choice exam. By randomly guessing from each question, from A, B, C, and D. In other words, you go and bubble in random letters for each of these 8 questions. Don't even read the questions. You've got to get done. You've got places to be, all right? And you're feeling lucky today. So that's the event that's going on, okay? So our first question here, keep the formula there for a minute. So question 1 will be, what's the probability, what is the probability you get exactly 5 correct? That's what we're asking. What is the probability that you get exactly 5 correct. Okay? Well, we've got to think about these numbers. We have to be able to tell you, these letters for the formula. So N is pretty easy because we've got 8 questions. You know that R is 5 because they're asking you to get exactly 5 correct. So it's 8 questions, 5 correct, which by the way means there's 3 incorrect. If you get exactly 5 correct, the other 3 must be wrong. Then what is P here? Well, a win, if you're randomly guessing, then the answer is right and the other 3 are wrong. So P is 1/4, that's winning. Losing, Q, is 3/4, or you could just do 1/4, or 1 minus 3, 1/4, which is 3/4. When I have these, I can apply the formula. The answer to this would be then 8C5, P to the 5th. Remember, these two always match. R goes in both slots. That's a key thing to the formula. And the other one, so think about this. I'm going to use another color here. These are the wins, and these are the losses. For us, P and Q, and this is where the subtraction comes in. 5 winners, 3 losing trials left. You missed 3 questions. Those two have to add up to 8. These numbers in here have to add up to 1. So we have 1/4 for guessing correctly, 3/4 for guessing incorrectly. So again, focus on that. These two, P and Q, must add up to 1. These two must add up to N. That's how you do this. And then we have to actually compute the numbers. Let me take a look at that. I need my calculator to do that. So let's see. 8 math C5. I get 56. There's 56 branches that do this. Now, 1 to the 5th is 1. I need 4 to the 5th. 1024. 3 to the 3rd is 27. 4 to the 3rd is 64. I can finish this by doing 56 times 27 for the numerator, which is 1512. And the bottom is either 4 to the 8th or 1024 times 64, depending on how you feel about it. 65,536. And there you go. That's how it works. So let's take a look at another one here, okay? Same event. In class, when you next sit down with me, we're going to talk about at least and at most. Right now, we're just doing the exactly. So let's do question 2 here. Question 2. What is the probability of getting exactly, let's say 4 wrong? In other words, getting 50% wrong. Okay? So the way we attack this, once again, is we need to know what N, R, P, and Q might be. We're also going to be calculating N minus R either here or over there. Because we have this formula, which is NCR, P to the R, remember those always match, and then Q to what's left. So that formula, I'm going to write it down again, and we just have to figure things out. 8 questions you guessed on. In this case, quote, winning is getting it wrong. We're asking about how many times, or the probability of exactly 4 wrong. So 4 wrong is the outcome you're looking for. So that's a 4. So wrong is 3/4 because there's 4 guesses. 1 of them's right, 3 of them are wrong. And this is 1/4. And in this case, 8 minus 4, if you were wrong 4 times, then you must have been correct 4 times. So here we go. We step over here, we do 8C4. We have 3/4 this time because that's what, quote, winning is here. And we want that to happen 4 times. And losing would be guessing correctly, and we did 8 minus 4, or the other 4. Again, you should note, these two have to add up to N, these two have to add up to 1. Now, the good news is that denominator is the same. It's 65,536, because even though it's 4 to the 4th and 4 to the 4th, this is 6th and 2nd. It's 4 to the 8th, if you think about it there. The numerator is going to be 8c4 times, well, that's a 1, because 1 to the 4th is 1. 3 to the 4 is 81. That one I know. Now, what is 8c4? We'll have to do that. So I have 8 math c4, 70. So I get a 70 there. And that's probably 5680 if we multiply it out. Let me see if I'm right. 70 times 81. Yeah, 5670, sorry. 5670. I multiplied out the top, which was these three things, and 65536. And that's the answer to this probability. It is a little bit more likely than getting 5. Okay. But not very likely. It's less than 10%. Ta-da. Last thing I'm going to say, if they said, what's the probability of getting exactly 8 wrong? You kind of don't really need this, because 8 wrong can only happen one way. That would just be 3 to the 4th time, 3/4 to the 8th. That'd be a slots problem. But if you did it 8C8, 3/4 to the 8, 1/4 to the 0, you get the same thing. This is me in front of the board where I belong. Hopefully this is you watching and understanding this. If you enjoyed this, be sure to like it. You don't have to subscribe to my channel. I'll never get to 1,000. I'll never be one of YouTube's stars. But make sure you come to class for when we look at the at least and at most stuff. And then down the road, we're going to be doing sample space with these and a whole cool meshing with algebra that you did. Most of you in Algebra 2, and some of you have done some of it in Algebra 1. This is Mr. Mistakis tipping his hat to you and saying, that's all.